Hello, everyone. Today, we're going to explore the fascinating world of cryptography, the core discipline that safeguards information security. In our digital age, whether it's mobile payments, online shopping, bank transfers, or signing electronic contracts, cryptography works silently in the background to protect our privacy and financial assets. Think of it as the invisible shield of the digital world. Let's pull back the curtain and see how this unsung hero, working behind the scenes, actually operates. By the end of this lesson, you will be able to 1. Understand the core objectives of cryptography, often summarized as 4 properties and 1 resistance: confidentiality, integrity, availability, non-repudiation, and resistance to attacks. 2. Distinguish between the principles and applicable scenarios of symmetric encryption, asymmetric encryption, and hash algorithms. First, what is cryptography? Imagine an ancient general using a coded book to deliver a battle report, writing "attack in 3 days" as raid of the 5th drum, where only those with a code book could decipher it. This wisdom of disguising information is the prototype of cryptography. Modern cryptography has evolved into a deep fusion of mathematics and computer technology. Its core objectives can be summarized as the 4 properties and 1 resistance. 1. Confidentiality ensures that information can only be read by authorized parties, for example, encrypted chat messages. 2. Integrity prevents information from being altered, for example, via hash value verification. 3. Availability ensures that legitimate users can access information and services when needed, for example, decrypting cloud storage data. 4. Non-repudiation ensures that an action or communication cannot be denied by its sender, for example, digital signatures. The 1 resistance refers to resistance to attacks, defending against various decryption methods, for example, post-quantum cryptography under the threat of quantum computing. When you use your phone for payments every day, have you ever wondered how cryptography protects your account? Let's dive into the 3 major schools of encryption technology: symmetric, asymmetric, and hashing. 1. Symmetric encryption, the representative of speed and efficiency. Principle: encryption and decryption use the same key, secret key, much like using the same key to lock and unlock a door. Typical algorithms are as follows. 1. DES, an early standard, but its 56-bit key has been cracked, for example, by the Electronic Frontier Foundation in 1998 in about 22 hours. 2. Triple DES enhances security by applying DES 3 times, but is less efficient. 3. AES, Advanced Encryption Standard, the current mainstream algorithm. It supports 128, 192, or 256-bit keys, and is widely used in Wi-Fi, banking systems, and more. Typical use case: when the company needs to send a sensitive file over the internal network, they often use AES encryption. If the company's finance department sends a payroll sheet to HR, both parties pre-share the secret key. The file is encrypted in ciphertext, and only HR can decrypt it back to plain text using the same key. Pros: fast encryption and decryption speed, suitable for large data volumes. Cons: high risk in key distribution. Asymmetric encryption, the cornerstone of security and trust. Principle: uses a pair of keys, a public key and a private key. Public keys are for disclosure, but private keys are for confidentiality. It's like a mailbox. Anyone can drop a letter in, encrypt with public key, but only the owner can open it, decrypt with private key. Typical algorithms are as follows. 1. RSA, based on the difficulty of factoring large integers. 2048-bit keys are widely used. 2. ECC, elliptic curve cryptography, achieves similar security with shorter keys compared to RSA. Representative use case. During online shopping, the merchant's public key encrypts your payment information, and only their private key can decrypt it. Simultaneously, the merchant uses their private key to create a digital signature for the transaction. You can use their public key to verify the signature's authenticity, ensuring the transaction hasn't been tampered with. Pros: secure key distribution, support digital signatures. Cons: slower encryption and decryption speed compared to symmetric encryption. 3. Hash algorithms. The digital fingerprint for data. Principle: maps data of any length to a fixed length string of characters. For example, SHA-256 generates a 64-character hash. It exhibits an avalanche effect. A tiny change in the input results in a drastically different output. Typical algorithms are as follows. 1. MD5, no longer considered secure. Collision attacks can be performed in seconds. 2. SHA series. SHA-256 is used in blockchain systems like Bitcoin. 3. SM3, a Chinese national standard cryptographic hash algorithm, is considered more secure than SHA-1. Typical use case. When you register on a website, your password isn't stored directly. Instead, the system stores its hash value. Even if the database is leaked, attackers cannot reverse the hash to get the original password because hashing is irreversible. When you log in, the system hashes your input password and compares it to the stored hash value for verification. Pros: verifies data integrity, protects password security. Cons: not for encryption and decryption, only suitable for verification scenarios. Next, let's look at cryptography's combination punches. Hybrid encryption and digital certificates. 1. Hybrid encryption. The wisdom of leveraging strengths. Principle: combines the advantages of symmetric and asymmetric encryption. Use a symmetric key, like AES, to encrypt the data. Use the recipient's public key, asymmetric, to encrypt the symmetric key. Transmit both the encrypted data and the encrypted symmetric key. Typical use case. When using a banking app to transfer money, the transaction data is encrypted with a fast AES key. This AES key is then encrypted using the bank's RSA public key. Both of them are sent together. The recipient bank uses their private key to decrypt the AES key, then uses that AES key to decrypt the transaction data. This ensures both speed and security. 2. Digital certificates. The ID card of the online world. Principle: issued by a trusted certificate authority, CA. A digital certificate contains the public key, identity information, and a digital signature from the CA. It solves the problem of how to be sure a public key truly belongs to the intended party by providing a trusted verification mechanism. Everyone, the future of financial security urgently needs professionals skilled in post-quantum cryptography. This represents a new career opportunity for you. Remember, cryptography is not only just about technology, but also it's the bedrock of trust. From ancient battle reports to blockchain finance, it consistently safeguards the security and order of human society. I hope that through today's lesson, you've not only grasped the basics, but also felt the charm and responsibility this field entails. Finally, please complete the following exercises. That's the end of today's lesson. See you next time.